Okay, this is Chapter 1 homework for Physics 201. I have a motorcyclist driving in a 60-kilometer-per-hour zone, hits a stopped car on a level road. The cyclist is thrown from his bike and lands 39 meters down the road. Was the cyclist speeding? You want to find the minimum speed he could have been going in order to have this accident. So basic projectile motion problem. This is where my cyclist launches into this parabolic path. And I know that if this is x naught equals 0 meters, that he lands x equal 39 meters away. But largely, I don't know much else. Now, there is one other thing that I can assume, and that is in order to find the minimum speed, that means that we want to find what speed will give him this maximum range. In order to get maximum range, this angle for his initial launch has to be equal to 45 degrees. All right, because if that gives us our maximum range, and so the minimum speed will get him to this 39 meters. All right, so I can assume that, and then I also know my acceleration in both directions. AY is minus 9.8, and AX is 0. But otherwise, that's all I know. So I'm going to say that at the top of my trajectory, I'll call this V top in the y direction, that's equal to 0, because when something goes to the top, it halts and then it starts coming back down again. Now, I can also say that I'm going to write my equations over here to the side. V, just like we did last chapter, V equals V naught plus AT, and then X equals X naught plus V naught T plus 1/2 AT squared. That's also true for the Y motion, that equation. All right? So in the X direction, since AX equals 0, I can say that X is equal to V naught T, and since that acceleration doesn't change, I can just say that's equal to Vxt. So X equals the velocity in the X direction times time. And then further, I can also say that Y is equal to V naught YT plus 1/2 AYT squared. All right, so these two are relevant in this case. And then I can also write this equation in terms of its Y components. This is similar to what we did last chapter, except I'm just making distinctions between the X and Y motion. It should be the Y. V naught Y plus AYT. So just sort of keep those off to the side and we can think about them as we go along. All right. So further armed with this information that the velocity in the Y direction at the top of the trajectory is 0, I can say that velocity at the top equals V naught sine of theta, all right, because that is the Y component of my initial velocity, plus AY times T, and I'm going to call this T 1/2 because it's half the total time. All right. Further, I can take this equation right here, and thinking about this point, which is halfway, I can say that x over 2, that's half my total distance, right, because I'm looking at this point, which is half the total distance, is equal to V naught cosine theta. All right, that's my velocity in the x direction. That is this term times t. And what time do I use here for this point? Times t 1/2. In projectile motion problems, you'll often use this halfway point, especially if it's symmetrical. You'll use this halfway point because we know what the velocity in the y direction is at that point. It goes to 0. And that's very useful information when you're working through projectile motion problems. All right, so I have these two equations written. Let's see, I know x. I know velocity at the top in the y direction. But I don't know what v naught is. I know what theta is. We're assuming it to be 45. And I don't know what t is. So I have two equations with two unknowns. My two unknowns are v naught and, I'm sorry, this should not be a y here. My two unknowns are v naught and t, or t1 half in this case. So I'm going to solve this equation for t1 half through a system of equations. V naught sine of 45, going in and putting in that angle that we assume, divided by 9.8. Now, I lost a negative here because they cancels out, because AY is equal to negative 9.8. So you should go through that algebra on your own and just make sure that you get the same answer. And then I'm going to, I'll rewrite this over here, x over 2, that's 19.5 meters, equals V naught cosine of 45 times t1 half. Now I'm going to take this and plug it in there. All right, when I do that, I get 19.5 equals V naught cosine 45 times V naught sine of 45 divided by 9.8. All right, if I solve for V naught, I'll let you do this. V naught is equal to 20 meters per second. So I want to know, is he speeding? That is his initial speed. That is his speed at this point when he hits a stopped car. But I want to know, is he speeding? So let's just convert our 60 kilometers per hour into meters per second, or you could do it vice versa. That is converting, actually no, that is what I've done. I'm going to convert my 20 meters per second to kilometers per hour. So 20 meters per second. In 1 hour, there are 3,600 seconds. And in 1 kilometer, there are 1,000 meters. And that gives me the speed of the motorcyclist is 72 kilometers per hour. So that is greater than 60. So the answer is yes, he was speeding. That's a pretty basic projectile motion problem. Not the hardest that you have, and not the easiest either, but a good basic projectile motion problem. While exploring a cave, a spelunker starts at the entrance and moves the following distances. As I write these out, I'm gonna sketch out a vector diagram. He goes 75 meters north. He goes 250 meters east. You know, in your cardinal directions, we have north, east, south, and west. So he goes 250 meters east. It's not necessarily to scale. 125 meters at an angle of 30 degrees north of east. Now, when I talk about north of east, that means this angle. I have an angle north of east. So you start at east and you go north of east. All right, so 125 meters, 30 degrees north of east. This angle is 30 degrees, 125 meters, and then 150 meters south. Okay, so those are roughly the distances that the spelunker travels. Again, not totally to scale. The distances that the spelunker travels. And now I want to know the magnitude and the direction of the resultant from the cave entrance. That is, I want to know the magnitude and direction of that vector. All right, the magnitude and direction of that vector. I find the easiest way to do this, if you have just a basic vector problem, is to write out the x and y components for all the vectors. All right, so I'm going to go through. For the first one, we have an x component of 0 and a y component of plus 75. For the second one, we have an x component of 250, y component of 0. For the next one, we have 125 cosine 30 and 125 sine 30. And then finally, we have 0 and negative 150. Watch those negatives because they'll get you. All right, and then I want to add up each of the x and the y components. So I'm going to add up all the numbers in this column. And if I do that, I get 360. And then I add up the numbers in this column, taking the 150 to be negative, and I get negative 88. So if I were to write the displacement vector in IJK notation, it would be 360i minus 88j. And sometimes you might have vector problems that ask it to write it in vector notation, and you just write it that way. And if there's a z direction our vector in the z direction, that will be your k term. Okay, but in this case, I want to know the magnitude and the direction. In order to find the magnitude of d, use the Pythagorean theorem, square root of the sum of the squares, 360 squared plus negative 88 squared, though that negative is moot, you don't really need it because it goes away, and that gives you 370. All right, so that's my magnitude, and now I want to know the angle. Now, if I were to sketch out this vector, it would look like this. I'd have an x component of 360, so like right here, and a y component of negative 88. So my vector looks like this. So I want to know what is that angle. All right. So to find that angle, I do the inverse tangent of 88 over 360. See, because I have a right triangle here. I have 360 and 88. Tangent of theta equals opposite over adjacent. This is the angle theta. All right, so that's where I get that, and that gives me the angle, which I find to be 14 degrees. Now this is part of the answer. We need to define that angle about which axis. So it's 14 degrees below the plus x-axis. That is part of the answer. It's not just 14 degrees. Now there are other ways that you can define that angle. All right, you can define it. You'll see this in other problems. This would not be real practical, but you could define that angle from this above the plus x-axis. So like that would be what, 346 degrees. You could also define it from this axis, but this is, for this problem, that's the most obvious way to define it. But any of those would be correct. All right, which of the examples of vector addition are correct and which are incorrect? Remember, with vector addition, let's say that you have a vector A and a vector B. In the tip-to-tail method, this is A plus B. So let's find those that aren't following that model. This one doesn't follow that model. It should look like A, B, A plus B. Here, this is correct. Oh wait, no, is it? No, that's not correct, because A and B are coming head to head like that. But this one is correct. I have A, B, and then this is A plus B. So this is the only correct one. Following figure shows vectors A and B. Graphically calculate the following. You'll do this in lab, but and you might have it on the test too, probably in a multiple choice question. All right, so let's do A plus B. Just want to sketch out our vectors. There's my vector A. There's my vector B. So A plus B looks like that. This is A plus B. All right, A minus B. I do my vector A. And then minus B is just the opposite of B. So this is minus B. And so A minus B looks like this. B minus A. Similar. There's B minus A, just flip it by 180. And then this is going to be B minus A. Notice that B minus A is the negative of A minus B. You see that? B minus A is the negative of A minus B. B minus A is just flipped by 180 degrees by A minus B. And you can see that because B minus A is equal to negative A minus B. All right. What was that? Oh, negative 2B. Okay, so it's going to be B in the opposite direction and twice its original magnitude, negative 2B. And then A minus 2B. I'll do it over here. There's A minus 2B. B twice as long as it originally was, and in the opposite direction. And so this then is A minus 2B. All right, those are just sketches, and not necessarily to scale, but they're pretty good sketches. You can tell if it's wrong, if you've gotten it wrong. As I said, these types of problems you'll see in the multiple choice. You won't have a free response for this, but you will see it in the multiple choice, and you'll see it in the lab. We'll do it more rigorously in the lab. Our biologist is studying the motion of bacteria. Notes the bacterium at position R1. After 6.2 seconds, the bacterium is at R2. What is its average velocity in unit vector notation and the magnitude and direction? Let's go back to our definition of average velocity. V average is equal to delta x over delta t, which is, in this case, is going to be R2 minus R1 divided by delta t. So this is similar to what we did before in the last chapter, except now we're just dealing with vectors. Now, we treat it the same way. We just group our I, j, and k components all together. All right, you group all your x terms together, all your y terms, and all your z terms together. And so it looks like this. You're going to have 4.6 minus 2.2. That's this minus this. It's in the I direction. Minus 3.7j. There was no term in the R2 in the j, so it was 0j minus 3.7j, which is just negative 3.7j, plus 1.9 minus a negative 1.2k. And then that's divided all by our change in time, which is 6.2 seconds, which is given right here. So I can combine those terms. I get 2.4i minus 3.7j plus 3.1k divided by 6.2. This is in meters. This is in seconds. So it's going to come out in meters per second. That's going to give me 0.39i minus 0.60j plus 0.50k. That's in meters per second. Now, I asked for the magnitude and direction. The direction is a little bit complicated because you're dealing in a three-dimensional frame here. We have 3 dimensions. So not only do you need an angle for the x-y axis, but you also need angles to define from the other axes. So we're not going to deal with directions in 3 dimensions, but you do need to know how to find the magnitude of a vector in 3 dimensions. And it's just the Pythagorean theorem in 3 dimensions, and it looks exactly the same. So it just looks like this. The magnitude of average velocity is just equal to the square root of the sum of the squares. That's vx squared plus vy squared plus vz squared. So just like you would do it normally in just 2 dimensions, you just add on that z term. All right, so you do need to know how to do that, but don't worry about the direction for this problem, how to find the direction. It's not much more complicated than what you've done already. You just have to find the various angles from the various axes, from the 3 axes. So this is going to be the square root of 0.39 squared plus 0.6 squared, actually plus negative 0.6 squared, which is a positive number, plus 0.5 squared, and these should have zeros after them, and that gives me 0.87 meters per second. Brick is thrown upward from the top of a building at an angle of 25 degrees to the horizontal and with an initial speed of 15 meters per second. If it's in flight for 12 seconds, what is the horizontal displacement of the brick? How high is the building? And what is the maximum height of the brick in its trajectory? All right, anytime you have the time, that tends to make the problem a little easier, a little more straightforward. Though this is not a simple problem. Let's take a look at it. I always like to sketch a figure if it's not given, and I can define my coordinates and what have you. This is my ground. It's at the top of a building. So this is my building. I'm going to call this the height of the building. This is h. We need to know what h is. Ask. This is v naught. Follows a parabolic path like that. We want to know what is y max. I'm going to call this, at this point, I'm going to call this y naught, and we'll set it equal to 0 meters. 0 meters. Okay? Let's write our equations over here. Remember, these apply for both x and y directions. That is that v equals v naught plus at, x equals v naught t plus 1/2 at squared. Those are our general kinematics equations. In the x and y terms, we can say that vy equals v naught y plus ayt, y v naught y t is 1/2 ayt squared. And then we can also say that x equals vx times t. That comes from this equation, since ax is equal to 0. Those are your basic projectile motion equations. We also know the x and y components, cosine and sine. Go and write that. Vx equals v naught cosine theta, and vy equals v naught sine theta. Hopefully on the exam you won't have to go through writing down all these equations, but it might be useful when you're doing your homework just to do that. Let's write down what we know. We know that v naught is equal to 15 meters per second. We know that theta equals 25 degrees. That's this angle theta right here. We know that the total time is 12 seconds, that it's in the air. Y naught is equal to 0, which is by our definition. I can say that v up here, v at the top, in the y direction, that's equal to 0. All right, for reasons that we've talked about. When it goes up to the top of its trajectory, it stops in the y direction. Yf, the final y position, is going to equal negative h. So we'll find yf, and then from that we just take the negative of that number, and that'll be the height of our building. I think that's about all that we know. We know the accelerations. All right, again, this is probably a little more verbose than you want to be on the test, because on the test you're going to have to go through these types of questions pretty quickly. So, but for practice right now, just write down everything that you know about the problem, everything that's stated explicitly in the problem, as well as things that are assumed. All right. So, we want to know the horizontal displacement for part A, as we want to know what is x equal to. I already know that x is equal to vx times t. So that's going to be v naught cosine theta times t. I know those things, 15 cosine of 25 times 12 seconds. And that gives me x of 160 meters. So the distance from here to here is x, and it's 160 meters. Now I also want to know how high is the building, what is h, and what is the maximum height of the brick in its trajectory. Okay, in order to find the height of the building, this is a little tricky. How high is the building? I want to know what is y, what is the position y at t equals 12 seconds? All right, that's really the question that I want to know, because down here, I know that at that point, that t equals 12 seconds. So if I can find y at that point, then I know the height of the building. So, you know, with these equations, you can put in the time for any point during the trajectory and find the position, either the x or the y position at that point. So, you know, if I knew the time here, I could just put in that time and find what is the y position there. But I particularly want to know what is the position here. T equals 12 seconds. So I say y equals v naught yt plus 1/2 ayt squared. That's this equation right here. I'm going to go ahead and put in the numbers, though. That's going to be y is equal to 15 meters per second, cosine of 25 degrees, times t, which is 12 seconds, plus 1/2 ay is minus 9.8 times 12 seconds squared. Make sure you square that number, okay? When I put that in, I get minus 700. All right, that means that the height of the building is equal to 700 meters. All right, now for part C, I want to know what is the maximum height of the brick and its trajectory. So I want to find out what is the time at the top of the trajectory. That is, what time is it when it gets right here? So what is t top? You know, this might seem really obtuse to you or not very transparent, but as you practice through these problems, you sort of get the techniques. And this is one of the techniques, that the velocity at the top in the y direction is equal to 0. All right? So I can say then that v top in the y direction is equal to v naught y plus ayt. All right, and this is going to be my t top. This is equal to 0. As we set up here, this is equal to 0. And so I solve for t top, which is equal to negative v naught y over ay. That's negative 15 cosine 25 divided by negative 9.8 meters per second squared. This comes out in meters per second, so it gives me seconds in the numerator. And that gives me a time of 0.65 seconds. Now I want to know what is the position at 0.65 seconds. So I say y, v naught yt. I'll go and put in those numbers. That's 15 cosine 25 times 0.65 seconds plus 1/2 negative 9.8 times 0.65 squared. All right, and that gives me an answer of 2.1 meters. And now we need to just know what that means. That means that here, that y is equal to 2.1 meters. But I already know, see, this is my y equals 0. So that means this distance is 2.1 meters. But I also know that this distance is 700 meters. So my y max then, y max equals 700 plus 2.1, which is 702 meters. 702 meters. And so that's the answer for part C. Okay. Please find a car at distance w equal 20 meters from the base of a cliff, of height equal 100 meters. How fast was the car going when it went over the edge? Solve the problem symbolically first and plug in the numbers. It's often better to solve it symbolically first. That way it's easier to find mistakes. So let's just write down what we need. This is a significantly easier problem. I know that x is equal to w, which is equal to 20 meters. So x is 20. If I say that y naught equals 0, then y is equal to negative 100 meters. All right, that's taking y naught here equal to 0. so y equals negative 100, x equals 20. And I want to know, I also know that Vx is equal to V naught. That's because there is no angle to the motion, and so all of the initial motion is in the x direction. All right, so I can say that x equals Vx times t, and that y equals V naught y t plus 1/2 ayt squared. I can make some simplifications here. This is 0, so y is just 1/2 at squared. Now I'm looking for Vx, and I have it right here. But I have two unknowns in this equation. I have t and I have Vx. So I'm going to solve this second equation for t, and I find that t is equal to the square root of 2y over ay, 2y over a sub y, the acceleration in the y direction. I'm going to take this now and plug it in here. So I get x equals Vx 2y over a sub y. So now I have only one unknown in this equation. And I am looking, what am I looking for? I'm looking for Vx. So I solve this for Vx is equal to x times the square root of ay over 2y. I know these values. Ay is minus 9.8. Y is minus 100. So that gives me a value of 4.4 meters per second. And that's the answer. All right, baseball pitcher throws a pitch clocked at 73.3 miles per hour. He throws it horizontally. That means that the velocity in the x direction is going to equal the initial velocity. By what amount d does the ball drop by the time it reaches home plate, which is 60 feet away? Now, we need to make some conversions here, so let's just convert everything to meters or meters per second. Vx, 73.3 miles per hour. I will give you the conversion factors always. 1 meter is 3.28 feet. 1 mile is 1609 meters. All right. So $73.3 in 1 hour. There are 3,600 seconds. In 1 mile, there are 1609 meters. And so that's equal to 32.8 meters per second. Remember, we sort of had this reference of 45 meters per second is 100 miles an hour. So this is 73. It's about 33 miles an hour. 33 meters per second. I also want to convert my x, which is 60.0 feet, to meters. So I have 3.28 feet in 1 meter. Feet cancel. And that gives me 18.3 meters. All right, so that's the Vx and x that we know. We also know Ay is minus 9.8, and Ax is 0. All right, so the first thing I want to do is just find t, and then I'm going to find what is the y position after that time. T is pretty easy to find. We just say x equals Vx times t. So t is x over Vx. That's 18.3 over 32.8. That gives me my time, which is 0.558 seconds. So that tells me the time it takes to get from here to here. So I want to know what is the y position at this point, which is t equal 0.558. All right, so I just say y equals v naught yt plus 1/2 ayt squared. But as we already said, this is 0, so it's pretty simple. Just 1/2 minus 9.8 times 0.558 squared. I get 1.53 meters. All right, 1.53 meters. That's the answer. All right, you throw a ball with an initial speed of 10 meters per second at an angle of 30 degrees. It lands some distance away. What is the maximum height and range of the ball? This is similar to a problem we had before. I throw my ball here at an angle of 30 degrees with an initial speed of 10 meters per second. Follows a parabolic path. I want to know the maximum height and the range. So I want to know x, and I want to know y. Y? I want to know y. Okay? So I want to use this trick that at the top of the trajectory that Vy is equal to 0. And when I do that, I can find the time for it to reach that point where Vy is 0. And then since this path is symmetrical, I can double that time in order to get the whole time for the trajectory. So let's do that at the top. This is a pretty common trick in projectile motion problems. I say Vy equals V naught y plus AYT. And I'm going to put a little subscript here, top. All right, that means this goes to 0. And I have a 0 equals 10 sine of 30 minus 9.8 t top. Solving for t top, the time at the top of the trajectory, I get 0.5 seconds. 0.5 seconds to get at the top of the trajectory. Then I can also find what is the y position at that time at 0.5 seconds is going to be V naught y times t plus 1/2 AYT squared. That is 10 sine of 30 times 0.5 seconds plus 1/2 minus 9.8 times 0.5 seconds squared. And that gives me my y position, which is 1.3 meters. So at this time, which is 0.5 seconds, the y position is 1.3 meters. Now, I want to know what is the x position at this time, and this time is going to be 2 times t top, only because it's symmetrical, okay? Only because it's symmetrical, that the left side looks exactly like the right side. So this is 1 second. Actually, it's just be 1 sig fig, just 1 second. So I just say x is equal to Vx times t. That is 10 cosine 30 times 1 second. It takes 1 second to travel the full range. That's 8.6 meters. Okay, number 10, this is the last one. You throw a tennis ball towards a wall at a speed of 51 meters per second at an angle of 40 degrees above the horizontal. The wall is 20 meters from the release point of the wall. How far above the release point does the ball hit the wall? What are the horizontal and vertical components of the velocity as it hits the wall? And when it hits, has it passed the highest point of its trajectory? Look, there are 2 scenarios that we could have with this. Actually, there are 3, but we'll just consider 2. There's the ground, there's the wall, here's my tennis ball. All right. I can have that scenario where it hasn't yet passed its highest point, or I can have this scenario. All right, where it passes its highest point and then hits the wall. I want to find out, the third part of this is which of those scenarios is it? And we'll find that as we go through the problem. Part A, how far above the release point does the ball hit the wall? We don't know the time, so we need to find the time. What is the time when it hits the wall? Just write out the equations. That always helps me. X equals Vx times t. Y equals V naught y t plus 1/2 at squared, and Vy equals V0y plus at. All right, I know V0 is 51 meters per second. I know the theta is 40 degrees. So since I know theta, I also know V0y and Vx. And I know x is 20 meters. All right, so I want to know how far above the release point does the ball hit the wall. So I want to know what is the time at the wall. So I can use this because I know x and I know Vx. X is equal to Vxt. T is equal to V0, or excuse me, T is x over V0 cosine theta. That is 20 over 51 cosine 40. And that gives me a time of 0.512 seconds. 0.512 seconds. That's my time when it hits the wall. So I want to know what is y at this time. This is really the answer for part A. Y is equal to V0 y t. It's 1/2 ayt squared. That is 51 sine of 40 plus 1/2 minus 9.8 t, which is 0.512 squared. And I get 15.5 meters. That's 16.8 minus 1.28, which is 15.5 meters. All right, so that's the position, the y position, when it hits the wall in either of those two scenarios. That's y, 15.5. Now, I also want to know what are the horizontal and vertical components of the velocity as it hits the wall. Well, that's pretty simple now that I know the time. For part B, I just say Vx is equal to V0 cosine theta. Vx doesn't change, so it's 51 times cosine 40. I get 39.1. And then Vy, it does change. It's going to be V0y plus ayt. It's going to be 51 cosine 40 plus minus 9.8 times my t, which is 0.512. That gives me a Vy of 27.8 meters per second. So this is Vx and Vy. Now, let's take part C. When it hits, has it passed the highest point of its trajectory? This seems like a complicated question because, you know, we could find out what is the highest point of its trajectory, and that's not that difficult. You just find what is the time when v top is 0, right? And then you can take that time and say, well, is that bigger or smaller than this time? All right. And if it's bigger, then it has passed the top of the trajectory. And if it's smaller, it has not passed the top of its trajectory. Or you could also just say, well, look, my Vy is positive. All right. See, Vy is positive here. That's Vy. This is Vx. But over here, Vx is still that direction, but Vy is negative. So since Vy is still positive, that means that you haven't passed that top of the point. So the answer is, when it hits, has it passed the highest point of its trajectory? The answer is no. Let's do that first method where this is sort of an aside. This is not the easy way, but we could say, what is T-top? And hopefully verify this. What is T-top? Well, Vy at the top equals 0. So I say Vy equals V naught y plus AY t. So 0 equals 51 cosine sine 40, 51 sine of 40, minus 9.8 times t. So that's going to be 51 sine 40 over 9.8. I get 3.3 seconds. So t is equal to 3.3 seconds. That means that at 3.3 seconds, it's like over here somewhere. Well, you can't see that, but this occurs at 3.3 seconds. Or excuse me, t top is 3.3 seconds. We're like over here at 0.512 seconds, and over here we have 6.6 seconds. So you can do that calculation and find out what is t top, the time at the top of the trajectory, or as I said, you can just say, well, Vy is positive, so it has to be on the left side before it gets to the top of the trajectory. That's the more elegant way. All right, I think that's all.